Okay, today we're going to start moving on into, well, algorithms, which I guess is kind of funny that we're going to do algorithms and data structures, but if you think about it, it's hard to do much with data structures without algorithms. So we're at least going to touch base on some algorithms. First off, the standard searching and sorting algorithms, which are made for searching and sorting. All right, great. I'm assuming y'all did something like .contains in OOP, so it had to search for an item within your list. So we're going to go through different algorithms to do about it. Hey, look, objectives. I already talked about that. So search is just to determine if something's in a list. Okay, everyone got that? All right, good. Hasn't blown anyone's minds yet. They created, that's nice. All right, search by a key of item and key comparison. So what they're trying to say is, how do we compare different searching algorithms? Hey, look, there's different ways to search, but you didn't know that. Or maybe you did, I hope so. But you're basing it on how many times you have to compare against a key, based on your search algorithm. Of course, the worst search algorithm is if you have to go through the entire list, and it's at the very end, and you started at the beginning, then you had to compare the key against everything in there. And then what would be the big O of that one? See how many people are awake now. I'll even draw some on the board.
The number of elements you have.
Right, so if n is the number of elements, it's O of n, yeah. So. And you're searching for -3 and you decide to start at the beginning, you'd have to go through the entire list. So that'd be O of n. So that's what a sequential search is, also known as a linear search. You start at one side or the other and you go all the way through. This works for both arrays and linked list, because a linked list you start at one side, usually the beginning, but you could start at the end, although I don't know why you would. You start the first element and you go all the way through. It's iterative. It can be implemented with recursion. We haven't talked about recursion yet because I don't think this is a good time to introduce recursion, because it would be very, it doesn't give you much intuition about why recursion is a good thing. It's just like, okay, why would we do it that way? So we'll skip recursion for now. All right, the analysis, you have to go through the loop. Okay. All right. So if it's in, here we go, best case, worst case, and average case. So if you're starting at the beginning, if it happens to be at the beginning, then you only search once. That's great. If it's at the end, you have to go through in comparisons. But what's the average number of comparisons? Well, if you assume equal probability that it would be any element in there, then what they're doing is, given n searches, one of them would take 1, 2, 3, 4, all the way up to n. So they're summing up basically an equal distribution. Wait, have you learned that formula yet? Ooh, I don't think you have. Someone just say, oh no? Who said oh no? Was it you?
I was thinking it. Maybe you can read my thoughts now.
That was the one that said it.
All right. Have you seen this one before? All right. What is it? Yeah, see, so right.
Like that was-
This is the most, probably one of the most important formulas in computer science. What is it, by the way?
M times n plus 1 divided by 2.
Right. When you take discrete math, you will prove this. But right now, you just have to take my word on it. Sorry, guys. I don't have time. Well, I can do the induction, but we got other things to do. Or have you taken discrete math? Oh, okay, so that's why you know. Great. Why is this important? Hey, look, that summation thing is this top thing up here. All right. And there's the n times n plus 1 over 2. 1 over n, because we're dividing it by n, so they put the n right there. And now if you cancel it out, look, it's n divided by n, and then it's n plus 1 over 2. And everyone follow me so far? Good. And what's the big O of n plus 1 divided by 2? Good morning. they go in, right? Because we don't, the rest is kind of just constant. So it's a linear algorithm to do sequential search, even in the average case. All right. Everyone see how I came to this conclusion? Yes, no, kind of, maybe, sort of. It's 8:15. Hey, a binary search. Oh, this is good. So a binary search is going to require that the items are in order. And where's my eraser? Good, here's one. So that's not in order. So let's make some ones in order. Hey, let's add some negatives. How many do we have? 1, 2, 3, 4, 5, 6, 7. Let's add one more. All right, give me a negative number lower than negative 32.
Negative 42.
42. All right, that's the loudest one I heard. Whoever said something else, you were too quiet. Okay, great. So what a binary search does is let's do a search for, I'll call it a B search. We'll say that this is ARY. And what number do you want to search for? That's not the middle number. Which one? 5? Okay, great. Okay, so first thing it does, it looks at the middle number. In this case, it could be the 0 or the 1. So let's just favor the lower one. So it looks at the 0. Is 0 equal to 5? No. Since it is sorted, it then asks, is it less than or greater than? 5 is greater than. So forget that. And it's not that, so you actually now just need to look at this part. Well, it looks at this part. It favors the lower one, so it's going to look at the 5. Oh, wait, we found it. Okay, that was fast. Well, let's say it was looking for the 1. Nice and squeaky today. If it was looking for the 1, it'd look at the 5 and go, nope, it's not the 5. Is it lower than or greater than? It's lower than. All right, great. Oh, look, there's only one element left because it cut out all of this. Do y'all see what the idea here is? You look at the middle, and then you cut the lower or the higher. Would this work if it was unsorted? No, because you can't assume one or the other. All right. So what's the runtime complexity of this one? Those who haven't taken the course before. Is this going to be faster or slower than linear search or sequential search? Faster. Why do you think it's going to be faster?
You don't have to go through as many elements in the search.
That's true. So it's, what is it doing each time to the number of elements?
It's cut in half.
Cut in half. All right. So with 8, it might be hard to see the benefit, but let's do 2 to the 20. Anyone know what that roughly is?
A lot.
It's a lot. It is a lot. It's roughly equal to just over 1 million. I don't have that number memorized. You can go look it up. But it's a little over 1 million elements. The reason why I put it 2 to the 20 is very simple. What's 2 to the 20 divided by 2?
It's still very large.
2 to the 19.
It now equals 2 to the 19th. So one search dropped it to 2 to the 19th. You divide it by 2 again, you get 2 to the 18th, dot, 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 dot. So how many times are we going to have to do a search for 1 million items? 20 times. Did y'all see that? That's why I wrote it to the 20th, so it could be easy to see this mathematically what's going on. And that was just over 1 million. If it's somewhere between 2 to the 20 and 2 to the 19th, it's going to take 20 times because it's cutting in half each time. So for 1 million items, it only takes 20, but our linear search would take, right, more than that. max of 1 million, on average, 500,000 or 500,000, which is a significant difference.
Yeah.
Yeah, right, a huge difference. By the way, we could also do 2 to the 30th, which is roughly equal to 1 billion. But now you can see how many elements that's going to take, 30. But for linear, it would take 500 million. If I do 2 to the 40th, that's a little over 1 trillion. Again, 40 times versus half a trillion. All right, hopefully you see that is crazy difference now. Obviously for 8, it doesn't pop out that it's that much faster because of how small the data set is. But if your data set starts to get large, it's very quickly, there's a huge performance difference. All right, any other guesses about what the big O would be? So let me put it this way. Is binary search O of n? No, definitely not. So it's going to be something lower than that. Let's see what the slides do. Oh, they're going to go through another example. Good. Let's do another example so everyone is on the same page. Notice that here's an array. Again, it is sorted. It has to be sorted. It's going to look at the middle number. This time they chose the 5, which is fine. And they're searching for, they're not telling you. That's cute. Searching for a value 75. Well, they looked at the 39, said it's not that one, must be greater. They chop off that list, and they only look up here from 45 up to 95. Okay. Oh, well, thanks. So if an L list has 1,024 elements, that's 2 to the 10th elements. I knew that one. By the way, if you multiply 2 to the 10th times 2 to the 10th to get 2 to the 20th, it would be 1,024 times 1,024, or whatever that is, which is a little over 1 million. A little over 1 million. At most 11 iterations needed to find X. They were including the first one. In this case, at most 22 key comparisons. All right, where are they getting 22 from? Well, when you compare against 39, you're technically comparing twice. One for equality, and then one if it's greater than or less than. So there's 2 key comparisons there. So it's actually going to be 2 times whatever. So up here, back on my board, for key comparisons, I was doing this to make sure it was clear what was happening, but the numbers are actually 40 and 60 versus 40. I mean, 500,000. That's still a crazy difference. It's not like that has changed that much. All right. So it ends up being, oh, they just tell you. It's a log. It's logarithmic complexity. Different way, right now you have not, I can't assume you've taken discrete math, so we can't sit down and do the math to formally prove why this is the case, but I'm going to try and give you some intuition because you need to be able to quickly recognize when an algorithm is logarithmic. First off, if it's cutting it in half, it's log base 2. Now, that's cutting it in half. If you had an algorithm where it looked at the thirds and chose which third was correct, that would be log base 3. If it was looking at it in fourths and it was choosing which one of the fourths to go, that'd be log base 4, et cetera, et cetera. If it was chopping it up into 1,000 and it was picking which of the 1,000, it'd be log base 1,000. So in half, it's chopping up into 2 sections and choosing which half to look at, so that'd be log base 2. Bless you. Another way to do it, intuition, well, this one is it chops it in half. Another way to look at it in half is if you have a for loop and the iteration is multiply equal 2. That means it's going to jump to a power of 2 somehow, by 2. Either it's multiplying by 2 or it's dividing by 2. That's also going to probably, and I have to say probably on this one because there's other tricks, but probably that's log base 2. And for this class, I'm going to make sure that is true, just to keep things simple. When you take discrete math, we will be able to formally prove this, and then algorithms, the professor will make sure you fully understand how you can derive logs. But for now, those 2 tricks will work for this class. I feel like I just got on a soapbox. All right. Okay. Okay, great. How are we doing? Y'all ready to code this?
I mean, I'm alive.
You're alive? Who's ready to code this? Everyone? All right, let's go code this.